To start off today, we're going to talk about something called valence shell electron pair repulsion. So what this is a term, if you want to Google it, it's VSEPR, VSEPR. You'll hear this term a number of times throughout the semester. What this represents is what shape our molecules are going to take. So we looked at Lewis structures earlier, where we looked at where all the electrons went. But so far we haven't talked about, well, how do these things actually arrange themselves? Do I know if this atom's on top of the other atom? Is it to the side? Does it make a ball? What shapes do they make? Now, the short version of why we care about this is it helps us make predictions. For example, how likely are two molecules going to interact? If I literally put them next to each other, will they fit? And that will be related to things like shape. You may have heard the term in biology sometime, form and function, right? That they end up being related to each other. So we want to know how our atoms are arranged to understand how they might interact in other cases. So this is why we're going to worry about what the shapes of our molecules take on. This will help us in some different ways as you go throughout chemistry. So to be able to talk about this, we're going to talk about something called an electron group first. So just so you know, it's going to feel like a tangent for a second, but the goal of this is I need to tell you which shape to use, and it's going to be based on the number of electron groups is how we figure out which shape to look at. So what is an electron group? That should be an E. So an electron group is going to be one set of electrons, or however many electrons we have in this group, that are going to try to arrange themselves to be as far away from all the other valence electrons in the atom. So you may guess from the name of this, it says valence shell electron pair repulsion. It's about valence electrons trying to stay away from each other. So this theory, VSEPR, is going to be that molecules will take shapes where all the electrons in the valence shell are going to stay as far away as possible. So the electron group represents each group that's going to try to stay away from all the other groups. So the way we know if something is part of an electron group is either it's a lone pair on the central atom. So we're not worried about things not on the central atom here. Or it's one or more bonds to another atom. So what do we mean by one or more bonds? So for example, if you had the molecule, let's say SO2, sulfur, double bonded to oxygen, single bonded to another one. If we had this molecule, this is its Lewis structure, we worked on it last week. This sulfur here is the center atom. We want to know how many electron groups does that center atom have, and that's going to tell us which VSEPR shapes to use when we get to those. So this atom is going to have 3 electron groups. And those are going to be, we have this single bond here, that's 1. This lone pair here, that's 2. And then you have this double bond here. We count that as 1 electron group. That's the only place where it's really different than any other type of label that you were using before, where a lot of times you might think of those as 2 separate sets of electrons. But they have to stay together here. The reason we group double and triple bonds as 1 is that it's about the electrons trying to separate from each other and stay far away. Well, both of these electrons are connected to this oxygen. This oxygen can't be in 2 places at once. So I can't split the oxygen in half and put one oxygen on one end of the molecule, that same oxygen on another part of the molecule. It has to stay in one spot. So both of these bonds have to stay connected between this sulfur and this oxygen. So this oxygen can only be in one position. So it only needs to try to separate that one part. Like this double bond, it'll stay together and stay formed to this oxygen. Whereas this lone pair up here can get far away, and this oxygen can get as far away as possible from this other oxygen. So there are 3 things that are going to try to separate themselves in this molecule. This lone pair in blue, this single bond in blue, and this double bond in blue. All 3 of those are going to try to get as far away as possible to give the molecule the most space so that all the electrons have room. So the goal is it tries to figure out an orientation that would do that. And that's what we're going to look at now. What shape is, well, this molecule will be in a bit. But we will get to this molecule. So we're going to go through all the different shapes that our molecules can possibly take. So let's get to look at that. So initially, we're going to look at molecules that don't have any lone pairs on the central atom because those will be the easiest. So we're going to do them first. And then we'll go back to molecules like the SO2 where they're lone pairs, as that complicates the shape further. So we're going to start with molecules where everything is a bond. And when we talk about that, we're going to talk about something we call electron geometry. And in the next video, we'll get to another type of geometry and talk about how they're... Whoa, I got fuzzy for a second. So we'll be able to talk about how there could be differences, how there's something other than electron geometry. But this is going to be the shape the electrons take in a molecule. So this is sort of a colloquial definition. Molecule. So the goal is we're looking at the position of the electron specifically. Later on, we'll talk about another type of shape where the atoms are instead. So here we treat each electron. We want to know where it's at and how it's arranged. So we'll start. Before going through all of these in big detail, I'll mention that there's a table in whatever textbook you're using. So I'm making sure this is future-proof. So if you're watching me in the future, it may not be the one I mention here. But assuming you're in 2020 right now while I'm recording, we are using Tro's second edition. And in that, on page 232, there's a table labeled as 5.5. And if you're in the first edition, it'll be a slightly different page. I think that chapter number ends up being, I can't remember if it's 4 or 6. They changed the chapter numbers by 1, I think. I think it's 1 more. But either way, it'll be in the chapter on VSEPR when you're going over the shapes. It's after Lewis structures. And there'll be a table that sorts all of these. So every shape I'm going to show you is on a single page. And if you learn that page of shapes, you are good to go. What I'm going to do right now is go through those shapes and talk about them a bit, because I think they can be hard to visualize. Having said that, I encourage you to also look at the giant table in the book, because especially when we get to the structures that have things in 3 dimensions, where it's not just flat, it is easier to see their pictures than it is to see my drawings. I am not an excellent 3D drawer. I will do my best and I will talk through what I'm doing, but you can probably find better, I will fully admit. That's why we have books. They can draw it with a computer much better than I can draw it on this board. And there are people that can draw them great on boards, but I'm definitely not one of them. So, let's start with the simplest shape. A linear shape. This is going to happen when you end up with 2 electron groups. So for example, carbon dioxide here. Carbon dioxide has 2 atoms bonded to this C. So because of that, we have, I'll just keep these out, 1, 2 electron groups. It doesn't matter which one, I'm just showing there's 2. Note that we don't worry about these lone pairs on this oxygen. So there are 2 electron groups. And anytime we have 2 electron groups, they make a line. So without worrying about all the electrons we just have, it's drawn like this, where it's just a cross. Obviously, there's still a double bond here. But the important part is it's actually a line. And with that line, what's important is this right here is a 180-degree angle, because it's literally flat, like my arm. It goes from there to there. So we end up with a 180-degree angle, because that's half of a circle. And note, we do have to know the bond angles for these, as it will help us make some predictions later when we try to compare different molecules. We are worried about that. It's the best way for us to describe the shape is, oh, this is a molecule with a 180-degree bond angle. Now, so that was linear. That was our simplest shape. So now, let's add some more electron groups. Each of these is going to have more electron groups. That's what's changing. So let's say electron groups, we have 3. This will make a shape we know as trigonal planar. So with our trigonal planar shape, we're going to use the molecule BF3 as an example. So what happens is this is still a flat molecule. We get a boron with 3 fluorines that make a triangle shape. And if we do the lone pairs, we end up getting them exactly filled. So if you go through and do your Lewis structure, you'll get that. And then we don't have any lone pairs to put on the middle. So because it's flat still, we have 3 angles, and each of these is a 120-degree angle. What you may notice about this structure, and all the ones going forward, is you have to start by drawing a Lewis structure. So for the ease of describing these, because I don't want this video to be 30 minutes long, I'm going to draw each of these where I just draw the structure. But for solving a problem like this, you will need to start, draw your Lewis structure if it's not provided, and count the electron groups. So if BF3 had a lone pair here, it would have 4 electron groups and it would have a different shape. So you have to get the Lewis structure right to be able to then come up with the shape. Having said that, for assessment purposes, we will have some problems where you have to go through the whole thing, and sometimes I'll give you the Lewis structure and then ask the shape, because that way I can assess both. Do you know both of them together, and then do you know it by yourself? So that's for 3. So let's add another group. So we're just going to keep adding. So here we get to 4. This is a shape called tetrahedral. One of the significant parts here is now that we have 4 things together, we're going to use the molecule CH4 for this, it starts to get really crowded to make things flat. So if you try to put all 4, so that this is how we drew it in class early with Lewis structures, if you do this, there's a lot of space on this side of the board and behind the board, where if you put all 4 hydrogens in one plane, they start to bump into each other. So now what happens is these start to take on some 3-dimensional shape. So what we get instead of this is we have 1 hydrogen that occurs on top. You then have a carbon. You then get 3 bonds that come out at angles. So what happens is it forms a little tripod on the bottom. Now, this is one where it is by far the most difficult for me to draw visually for you. This is the one where I most recommend pause me and go look in your book at what this looks like. Or Google tetrahedral molecule, that's fine, or whatever search engine you like. Do that. It is hard for me to draw on a board. I will explain what it means, but I'll be honest, I remember trying to look at this when I was learning that. Looking at this picture at first didn't tell me much. I could tell you, oh, the professor told me. This little wedge thing means this hydrogen's coming out of the board at you. This dotted line here means the hydrogen's supposed to be going away and out of the board. And so 2 of the hydrogens are in the plane. Having said that, I realize that if you haven't looked at these before, I don't think that means a whole lot. So this is the part where you take a break and go look at a picture of one of these. Okay. So hopefully you have looked at that or you've seen it because you've read your book already. And what I want to mention here is also that these angles, if drawn just right, are all the same. They're 109.5 degrees. That was poorly written, 109.5. Everything else makes nice round numbers, things like triangles or circles or squares. This is the one that you have to memorize. It's a little different. So it's 109.5, and that occurs at all 4 angles that can be drawn. And so if you do it just right, any one of these hydrogens, you could actually flip the molecule and put it at top. So this hydrogen here, if I were to rotate the molecule, I could put this hydrogen on top, and then this hydrogen would flip down back into this position. So this is something where I think in time you will get it. But I will admit that at least for me, molecular shape was really hard when I learned it in general chemistry. So even when I played with a model kit with it and looked at pictures, it just took a while. And I think I got it better as I went into further chemistry classes. We deal with this a lot in organic as well. We'll talk about it in 1212. So I think the shape thing, especially for this tetrahedral molecule, can actually be kind of hard. Having said that, I do want to mention this electron geometry here is by far the most common you're going to see. And if you think about our rules, it can make sense because it's got 4 electron groups. Central atoms tend to want octets. So if my carbon wants an octet, if it's bonded to 4 different things, that gives it 4 electron groups. So you will see a lot of molecules with this structure, so I think it's worth looking at a picture and trying to get a feel for what it looks like. Now we've got 2 more that occur with expanded octets. So we can get more than 4 electron geometries, more than 4 electron groups, and we'll talk about those 2. So we could have 5 electron groups. That will be a shape known as trigonal bipyramidal. And I'm going to use the molecule PF5 here. So what happens now is, in the case of the shape with 4, they were in different orientations in 3 dimensions. But for 5 and 6, what happens is you actually have 2 flat shapes that intersect each other. So for the shape for 5, what you do is you take a trigonal planar molecule plus a linear molecule, and you add them together basically. So what do I mean by that? First, in the middle, you have a P, and it's connected to 3 fluorines. I'm not going to draw the lone pairs on the fluorines for right now. It's important to know they're there, and for drawing Lewis structures, you should always draw them. But for talking about shape, I'm going to temporarily not draw them. So we have this triangle, and so for the triangle, we have 3 fluorines, and the idea is this is a triangle, so if we think of it, it's like I'm in the middle, I have 1 atom out in front, and then I have 2 atoms behind me. Let's move it. So yeah. So imagine I'm like a superhero capes wouldn't work like that. Some shape, I don't know, you can come up, you can be creative. So I've got 2 fluorines behind me, and I realized the camera didn't work as well, and then 1 in front of me. Again, go look at a picture. Me trying to do the shape, especially in my kind of jerry-rigged camera setup, is not the best for that. So we have our trigonal planar. So I guess another way to think of it is, imagine it was on the board, it was flat from earlier, and we flipped it. So it was like this when we drew it on the board, and now we flipped it sideways. So we have it, the 3 fluorines, now sideways. And then what we do is we take our linear molecule and we jab it through like a stake. We jab it through the center of the phosphorus. So you put 1 fluorine on top and 1 fluorine on bottom. So you have a linear molecule, and you used it to jab your triangle in the middle. So you've got a triangle with a stake driven through it. And then you put fluorines on either end of the stake here, or whatever atom you're working with. And everything goes through this middle atom. So here, the bond angles. This is the only one we're going to look at where we have 2 different angles. So the triangles all make 120 degrees, like they did earlier. So these angles are on what we call the equatorial plane. So that's going to be the stuff that's going this way, side to side. So in that side-to-side plane, we have these 3 atoms. Then we jab the fluorine through the middle, and so the top and bottom are called the axial atoms. So that's in the axial. So these are the 2 axial atoms. So sorry, I'm not going to call it a plane. It is a plane, but the focus, I'm sorry, is on atoms. So these 3 are the equatorial atoms in the triangle. And these 2 fluorines on top and bottom. So your top and bottom atoms are always going to be your axial atoms. So if we're talking about the axial ones, they'll be top and bottom. Equatorial will be in the middle, kind of like think of the equator of the Earth, right? Center of the globe, things on that edge. This is like the North and South Pole. So here, if you remember your linear molecule was 180 degrees. But now you jabbed a triangle in the middle of it, which splits that 180 in half. So the axial atoms end up with 90 degree angles. So that's between, I'm going to draw another drawing where we can see it. That should be dashed. This should be wedged. So here we're just going to worry about the axial. So between here is a 90 degree angle like in a triangle, or between here. So if we look at this any of these 3 fluorines and compare them to the 2 axials, so if we do it between there, or if we're just looking at like the angle it makes, yeah, all 3 of those, the triangles that make there. So between this fluorine at top and the equatorial plane, we get a 90 degree angle. This fluorine on bottom, and these down here is a 90 degree angle. So technically, if you were worried about this fluorine, phosphorus, fluorine here, there are 180 degrees apart, but we're not going to talk about that angle that way because there's another atom that's closer. So we're always doing 3 atom sets that are closest together, rather than choosing things that are further away. So you end up as, this is the only molecule that ends up with 2 angles to know. This has 90 degrees and 120 degrees, both. They're both relevant bond angles for it. So that gets us through 5. So let's look at one more shape. I've only got 1 more to do. And depending on when you're watching this, I will mention there are some shapes we won't cover. You could look at 7 electron groups for some systems. We're not going to deal with any of those. We're not going to worry about it. But I will mention that if you Google some, you may find some charts that have a couple of shapes we don't mention. There aren't many, but there are 1 or 2, especially when you start getting into inorganic molecules, that will end up having more groups that we're looking at, or just a different number than what we're looking at. We're not worried about those, though. So you get to stop at 6 for electron groups. This is an octahedral shape. So we're going to look at SF6 for this. And again, I'm not going to draw the lone pair electrons on each fluorine. Each one ends up with exactly 3 lone pairs, so 6 lone pair electrons. And then the sulfur has 6 bonded fluorines and no lone pairs on it. So we end up with a sulfur, and the axial stays the same. There's 1 on top, and there's 1 on bottom. Then what we do is we make the bottom a square. The equatorial becomes a square. So the way to think of this is the 4 fluorine atoms end up getting into a square shape. So both these are supposed to be away from us. Both of these are away from us. So there's like a flat layer down here, but there's a sulfur in the middle, and there's a fluorine up here, back here, up here, and over here. So you end up with a square base. Then you have 1 on bottom and 1 on top. So that ends up making it's like 2 pyramids on top of each other. And it's called an octahedral because if you draw a figure between this fluorine, and this fluorine, you get a triangle. You do the same thing between this one, and And this one, you can draw a bunch of different triangles to connect these molecules, and you end up with 8 triangles when you connect all of them, 4 on top, 4 on bottom. They're basically 2 square pyramids that you put on top of each other, one upside down, obviously, because the squares meet. So that's why you call it an octahedral, is it has 8 triangular faces. Having said that, again, definitely go look at pictures, just like I said with the other ones. I know my drawing can't do it justice. This is what it will look like when you see it on a chemistry thing where it's flat on a board rather than trying to draw pictures of what these things look like. And all of their angles, since we have a square now, squares, if you split them in 4, have 90-degree angles. So these are all 90-degree angles. So that will cover all of our electron geometries. What you'll notice is we haven't yet talked about what if there's a lone pair. So in the next video, we'll deal with molecular geometries, which are shapes. Once we start putting lone pairs in the middle atoms, how that changes the shape.